Welcome to the Artificial Intelligence course, A Complete Introduction. I'm called Long, and I'm very glad to be with you in the lesson today about linear regression. You should know that linear regression is a very fundamental tool in supervised learning, with so many applications, notably in predictive analysis. And today, I will present to you the idea of linear regression and its problem formulation. First of all, we start the lesson by a real-world example. Imagine that you are asked to do a market research on apartment rent in Paris, and one of your missions is to analyze the effects of area on apartment rental. That means you have to find a mathematical relationship between apartment area and its rental cost. Then, I'd like to show you some real data that I picked randomly from a website in France. Let's look at the data table on the left. In machine learning, this collection of data is called dataset or training set. You can see that the table has two columns. The first one shows apartments areas measured in square meters, and the second column shows the corresponding rental cost in euros. For example, in the first row, with an apartment having only 9 square meters, the rental cost 550 euros, and so on. Next, we draw a scatter plot for the data in the training set, as shown by the figure on the right. In the scatter plot, each data point represents for a row in the data table. The horizontal axis is area in square meters, and the vertical axis is rental cost in euros. Normally, to do regression analysis, we often need a lot more data than that, but for the purpose of illustration later, I'd like to show you only a portion of the dataset, but you should keep in mind that there is a lot more data than that, okay? As you already understand the use case, we now move to the analyzing step. Remind that our mission is to analyze the effects of area on apartment rental. That means we have to find the relationship between these two variables. So, we let x denote the input area in square meters, and y denote the rental cost in euros. Then, we have to find a function f of x such that, given an input area x, f of x will be the predicted value of rental. Importantly, there are two cases with the function f of x. Either f of x is a linear or a nonlinear function. Maybe many of you already know what is linear and what is nonlinear, but some may not, so I will explain it briefly. If f of x is a linear function, then its equation will be f of x equals phi1x plus phi0, where the two real numbers phi0 and phi1 are called the parameters of the function f of x. Furthermore, the graph of this function will be a straight line as you see in the scatter plot. Definitely, different values of phi0 and phi1 will give different straight lines, okay? Now, in contrast, if f of x is a nonlinear function, that means its graph will not be a straight line, therefore it doesn't have this form. Actually, there are a vast number of nonlinear examples that I can show you, but I just pick a very simple one. F of x equals phi2x squared plus phi1x plus phi0. This is a quadratic function, and the graph of it may be a curve like this. Or, if f of x is a cubic function like this, you see, the highest degree is 3, so its graph may be something like this. And there are a lot more, examples of nonlinear function that I could show you. However, in this lesson, we focus only on the case where f of x is a linear function, and the other cases will be discussed in a future lesson. Actually, many of nonlinear functions, can be transformed to linear functions for regression analysis. So that's why linear functions have more interest to begin with. And you should know that when f of x is a linear function, this problem is called linear regression. And we say that f of x models the linear relationship between the input variable x and the output variable y. Okay, as you see, the idea of linear regression is to find a linear function f of x that predicts the output y. And I would like to remind you that the graph of the function f of x is a straight line, and we want this straight line to fit the data points. But how do we find the best fitting line, that is, the straight line that best fits the data points? Or equivalently, what are the best values of phi0 and phi1? Because different values of phi0 and phi1 give different straight lines. For example, if phi1 equals 0 and phi0 equals 1000, then f of x will be 0 times x plus 1000. So f of x equals 1000. Then its graph will be a horizontal line like this. But it doesn't look like a good solution to our use case. Let's try again with other values. phi1 equals 100 and phi2 equals minus 1400. Then f of x will be 100x minus 1400. And its graph will be like this. However, it still doesn't look very well to fit the data points. Now, I'd like to try with phi1 equals 30 and phi2 equals 300. Then f of x equals 30x plus 300. And you see, this straight line looks better. But how can we know that it is the best fitting line? Because we can have so many solutions like this. Therefore, we have to define a metric that allows finding the values of phi0 and phi1 that give the best fitting line. Let me show you how. First, assume that we have found a solution f of x equals phi1x plus phi0 that gives a straight line like this. Then, for any data point xi, yi from the training set, where I is the index of sample data, and m is the total number of sample data in the training set. Let y hat I equal to f of xi, which equals phi1 xi plus phi0. That means y hat I is computed from the linear function f given x equal to xi, okay? In this context, xi, as you know, is our input variable, and yi is the actual output corresponding to xi, because it is the true output observed from the training set. But y hat I is called the predicted output. Is indeed the value of the function f given the input xi. And the difference between the actual output and the predicted output is called error. Obviously, if f of x is the best estimator of y, this error must be close as much as possible to 0. In other words, the best fitting line or the best values of phi0 and phi1 will minimize the difference between the actual output and the predicted output. To give you more intuition about this, let's look at the scatter plot. I will take a data point xi, yi, for example this one. In this example, xi equals 40 square meters and yi equals 1600 euros, okay? Now, look at this red point. It is the predicted point of xi, yi given the solution f of x equals phi1x plus phi0. Please note that the coordinate of this point is xi, y hat I. Then, this difference between y hat I and yi is called error, and it is the value that needs to be close to 0. In the same way, we calculate the estimation error for all the data points in the training set like this and try to find the linear function f of x such that these errors are minimized. With this idea in mind, if we define a cost value like this, cost equals 1 over m sum from I equals 1 through m of square errors. This is called the mean square error for all the data points in the training set. Then, our objective is to minimize this cost value to find the best values of v0 and v1. For some of you who may ask why we have to square the errors like this, let's look at the difference of yi and yi. This may be positive or negative, and if it is a negative value, that will not make sense when we want to minimize the errors. So that's why we square the errors like this. Of course, there must be other reasons for doing that, but I'd like to encourage you to search it on the internet by yourself. Okay, this is the idea of linear regression. Now I would like to give you a recap as follows. Linear regression is the task of finding the linear relationship between one or more input variables and one scalar output. Especially, if there is only one input variable, the problem is called simple linear regression. Otherwise, if there are more than one input variables, it is called multiple linear regression. In our use case example, there is only one input variable, as you see, the input area of apartment. So, this is absolutely a simple linear regression problem. And to find the linear relationship between an input variable x and an output variable y, we have to find a linear function f of x equals v1x plus v0 that approximates the output y. Concretely, the graph of this function is a straight line and we want it to fit the data points. And to find the best fitting line, we have to find the values of v0 and v1 that minimize a cost function which is equal to 1 over m sum from I equals 1 through m of square errors, where yi is the value of f given the input xi. Indeed, to deal with such kind of optimization problem, one of the most popular approach is to use gradient descent. But we will discuss about this technique in the next lesson, the second part of linear regression lecture.